To the June meeting of the Madison Astronomical Society. We're running a little bit behind, so I will just zip right in. Are we on the air? We are on the air. And as for those of you who are not familiar, we are broadcasting on our YouTube channel live. So if you're in a situation where you can't make it, feel free to join us online. Um, we have a bit of special business today, and I'd just like to begin handing these out, and I want to make sure the secretary gets a copy. We have a couple of items of business where we would like to uh, we have uh, a proposal to merge the yeah, it's hard for me to I was in the UW marching band for 7 years and I can't talk and do things at the same time, but I can play a horn and march a drill just fine. It's incredible. But anyways, we have a proposal that was made over the last couple of months to essentially in the past we've had uh, separate tiers for regular members and as we see here, here's the general membership, which we would call a regular membership. And we also used to have an observing membership. So if you were either uh, a student member, if you had a student membership, or you were uh, part of the general membership, you had the option to pay an extra fee to get the observing privileges, which basically the observing privileges was the right to be able to use the observing facilities that we have down in Greene County at Yana Research Station. Um, what we would like to do is merge, essentially make the observing membership as shown here obsolete and delete it from the proposed bylaws here we go again. Uh, yeah, Kevin is handing out to you right now. We want to delete observing membership from that. And we want to give both the regular general membership and the student, as shown here in the yellow highlight, the observing privileges to everyone in the general membership and in everyone who has a student membership. Now, to make that happen, we're also, instead of having or an observing membership tier for a total of $70 annually and a regular tier at $30 annually, we are there's a proposal on the table to uh, have a single tier of membership of $60 for annual tiers, and we're going to increase instead of having the observing student membership at 45, we're going to have a student annual a student membership with observing privileges at $30. Does anyone have any questions so far? All right, so in this slideshow, I'm just basically showing, here in Article 3, Section 1, are just all the changes are highlighted in yellow here. We've got the old language from the General Assembly. And all we're doing is just tweaking a word here to make it clear that all the memberships that follow this section, that what it says in the under General Assembly applies to all those memberships unless written otherwise. So see if you're a household, so if you're a household, um, oh, there's something missing from here that I missed. If you're in a household as it's shown in the copies you have, living at the same address, um, you will have all the members of the household. All you have to do is purchase one membership, but then each membership gets one vote for the entire household. So that's all this is really saying. With the following classifications. Now, as I said, we've got the general membership now is going to have, with whose family members live at the same residence. That's the part I was talking about. Um, a single general membership, all the family members in that general membership shall have the privilege of using the observing facilities. And that's basically carrying over to the new language under student membership. So all we're basically doing to the student membership is adding this tier. And the only other change we had to make since uh, observing membership is now obsolete, we had to go to the honorary membership and change that from observing membership to a general membership. So those are basically and all the changes with the exception of observing membership is just going to be completely gone now. All right, is there any questions or discussion? Okay, well, first of all, I almost forgot the most important. I'd like to uh, call to order a meeting of the General Assembly of the Madison Astronomical Society at 7:24. I would like to open the meeting. Do we need any additional discussion or recapitulation of what I just brought forth? Yes, Wayne? Yes, Rick.
Vertical lines, section two, any activity that produces a Hub's principle. Does anyone in the room care that it's the wrong principle?
Oh, yeah. Yeah, that's something I think since, I'm not necessarily a lawyer or anything, but when it comes to things like SOPs, I work at a highly regulated laboratory, and our SOPs are essentially legally binding, and I don't think minor typo corrections like that would be categorized as an amendment. So it would just be a matter of, Dan, could you jot down a note kind of highlighting that principle and
What page and where? It is part of the line, section two, it's just over halfway down the paragraph. Okay. Principal to principal.
yeah, thank you very much.
You're reading the whole thing here. I used to be a copy editor, and these things just.
Yeah, no, and a judge would probably grimace and raise an eyebrow if he read that in the court. Yes, you're good.
That's the first thing I wrote in the paragraph. Maybe it's great.
Yeah, yeah,
I worked at university. We used Microsoft Word, and I had to write Baskin Ball a lot. I don't know. And every time I did it, Word wanted to change Baskin to bosom. Yeah. Well,
all right, yes, Kevin?
that's this walks. In Article 1, the dates in there, I thought we had questioned this before.
Well, I would like to limit, we're not, I'm sorry to interrupt you, Kevin. I would really like to limit the scope of this discussion of the bylaws to the subject at hand.
But if we're gonna change the bylaws, I think that there is a flaw. Because it says that the accountable report shall be from October 1st.
Yeah, however, the proposed change has not been, the membership has not been given at least a month's notice to consider the change.
So we can kind of put that on, if we wanna, or want to set up a list of changes to have it ready for the May general membership meeting next year.
Right, because I think that was one of the things we're talking about, and there were some other things that we're talking about in the rest of the bylaws that aren't part of the scope. Yes, John?
I would like to make a motion to approve the change as outlined by the presentation.
Do I hear a second to the motion? Kevin Santula, second the motion. Is there any further discussion? Hearing none. All those in favor of the motion on the table signify by saying aye. Aye. All those against the motion signify by saying nay. It's the opinion of the chair that the motion is carried. All right, the second item of business. So it also requires per the current bylaws that the proposed new membership due structure also needs to be approved by the general membership. Concerning the new $60 membership tier for the general membership and the student membership tier at $30, all annual fees. Is there any further discussion?
We would move that we adopt the new fee structure, $60 for general membership and $30 for student memberships. Second.
Okay, I hear a first and a second. Is there any further discussion? Yes, Jurgen?
Yeah, I just want to say that the subtext of this is that the membership dues would be effective as of October 1st.
That's correct.
I would like to suggest that since we're doing this now, any new memberships can come in under this. It's just going to make my life a lot easier.
Right. Does anyone object to that idea?
I so move.
I guess by unanimous consent, I guess, yeah, that we could, if people want to say, and I think we've traditionally done that when people sign up late in the term. they're just grandfathered into the following term?
Close enough to mini membership, yeah.
All right, so be it. Is there any,
I'm taking notes and it's happening fast.
all right, all right.
It's effective immediately?
Effective immediately. Yeah, let me know when you're ready. And in case there's any further question, I do believe that this meeting is being recorded on YouTube.
Okay. Okay, go ahead. So we have a motion, a second, we have the discussion, unanimous consent, and we need a vote now?
Yes, I believe so. Is there any discussion, any more discussion or any objection to making the new fee structure applicable immediately? All right, hearing none. All those in favor of the motion signify by saying aye. Aye. Those against the motion signify by saying nay. It is the opinion of the chair that the motion is carried. All right. Is there any further business that needs to be discussed? I do believe we verified that there is a quorum here tonight. So do I hear? Oh, yes, John.
Move to adjourn.
But someone second? Who seconds? I think Rick's hands up was first. Quickly. All those in favor of adjourning signify by saying aye. Aye. All those against signify by saying nay. Hearing none, the meeting is adjourned. Thank you very much, everyone, for being here.
6 minutes.
All right. So yeah, I see that is actually after 7:30. I am going to. We did send out this month's announcements by email. Is there anything anyone wants to just quickly bring to the attention of the club? And if anyone's interested in what's coming up, please check your email and read the email newsletter that was sent out last Sunday. All right, so I guess it's time to introduce tonight's guest speaker. John, would you like to introduce him for the people here? Give you my microphone.
Before I introduce John Rudolph for tonight's meeting, I'll just tell you a little bit about next month. The July meeting, July 12th, I want to say, we're having a guest speaker we've had many times before. His name is Bob Benjamin. Bob is a professor of astronomy in the department here in Madison, as well as at Platteville, where he teaches physics. Bob's research has centered on the structure of the Milky Way. Bob is one of those guys who has done a lot of work in really defining the exact spiral nature, the central bulge, and so forth of the Milky Way. Bob has teased me for a couple of months now that he's been embargoed because they are publishing a paper this summer that has some striking new news. I don't know what it is, but he's going to come talk to us about whatever it is next month. So Bob is going to give us some cutting edge updates on the structure of the Milky Way. So that's July. Tonight, I am really pleased to introduce, and John, yeah, go ahead and get plugged in. John Rudolph is a professor in, is it curriculum and instruction at the university? His specialty is science education. John came up through the ranks as a middle and high school science teacher. Um, Close to my heart because I'm an educator and we've got some science teachers in the room too. And he has basically done a lot of research into the foundations of science education. And he's going to give a talk tonight on what he's found, what he thinks is important, and what we should all think about in a climate where expertise is under attack in many ways in our culture, you may have noticed. So please give a warm welcome to Dr. John Rudolph. Oh, and I'll say, John is happy to take questions, but we're going to ask you to hold your questions until after his presentation, and I'll have the microphone, and I'll come around and get your question on tape. Thank you.
Okay. Thanks, John, for the introduction. It's very nice of you. And this is just from the business meeting part of this. This seems like a really fun group. Um,
Join the board.
yeah, thanks so much for inviting me, John, to share some of the work that I've done and what I'm doing. It's really interesting. I spent some time then going into the Madison Astronomical Society. I wasn't aware of it, and looking at the history, and history of science is something I'm interested in. And I was really surprised to learn this group goes back to 1935, and so it's nice to now be a little part of that history by being here today. So thanks everybody for coming out. I appreciate that. Um, so the topic of the talk here is the three myths of science education, and I'm going to start by just providing a little context. So science education research is my area, and if you look at sort of current science education research, a lot of it takes place at the micro level of student engagement and classroom practice, things like that. You see research studies on students learning through data, exploring model-based curriculum materials, engaging with scientific practices, and things like that. But my plan today is to step back to a much larger grain size. And what I'd like to do is challenge some of our assumptions about science education. And these challenges come into what I call the three myths of science education. Um, and I'm going to start from two distinct sets of ideas and then see how they come together and how they might or might not be reconciled with one another. Um, this is essentially what I do in my new book, Why We Teach Science and Why We Should, which came out last year, Oxford University Press. And if you're interested in some of the details of the points I make today, this is where the essential arguments come from and where you can find the references to the research and so on. So the first set of ideas in this book, chapter 1, I focus on purposes of science education. That is, the reasons we say science learning is important. And these would be the purported benefits that accrue to the individual or society from having students learn science in K-12 settings, middle and high school is what I'm looking at. And the second is to outline what many of us would consider to be an ideal science learning environment, both in terms of content and process learning. And then I'm going to put these two things, and so that's what I call what we actually teach ideally in typical science classrooms. And then I'm going to put these together to see how the ideal science learning environment matches up to the justifications that we offer for science education in this country, and in fact, in many Western countries. And specifically, I'm going to draw from the relevant empirical research to essentially test our assumptions about what we think science education accomplishes in actual practice. So just to be clear, in outlining the commonly voiced purposes of science education, I'm not assuming that any of you individually hold these necessarily. My point is only that these are the generally accepted reasons why we say we teach science in schools, often voiced in policy documents, parents, even by practicing teachers. And the same holds true for the ideal science learning environment part of the picture. Again, this is sort of a large grain size, big picture. So let's start with the purposes of science education. A lot of my teaching is involved in the teacher certification program at UW-Madison, the secondary science program. And our students now come in with undergraduate degrees in science completed. And our program is a 13-month master's with certification, the secondary level. And when the students come in the methods class in the fall, the one that I teach, I have them get in groups and come up with why do they think what do they think is important about teaching science? And so this is from the last fall's class. They get in their groups, then they report out, and I write them on the board here. And it's interesting to see what they come up with. These students have been highly successful in their own science learning journeys and are committing themselves because of their enrollment in our program to careers as science teachers. So it's really interesting to see what they see as the value of science for their students. And you might not be surprised. You can see things up there like help students prepare for science careers, improve health and wellness, promotes better decision making for citizens, preparation for college science courses, economic prosperity, so on and so forth. Similar lists have been developed over the years by a host of science ed researchers. One of the most comprehensive is that offered by George DeBoer. He was at AAS in Project 2061 for a number of years. And he came up with a list of 9 things, goals of science teaching, and they're the same kinds of things, right? Uh, Teaching and learning about science as a cultural force, preparation for work, informed citizens, and so on. And I've been through these lists again and again, and it seems to me that they can be distilled to essentially 4 primary goals, or aims, or justifications for teaching science. And for me, these would be science education for culture, science education for better thinking, science education for utility, and that breaks down into personal utility and then sort of national level, national security, economic growth kinds of things, and then science education for democracy. And I want to give you a sense of what I mean by these things, so I'll take them one at a time. And the first one, science education for culture. This is, and I think John maybe mentioned this, he was talking about Carl Sagan. This is sort of the Carl Sagan reason, right? Teaching science to convey a sense of appreciation at the wonders of the natural world, the beauty of crystal formation, the profound length of deep time, the amazing adaptations of living creatures, as well as the ability of the human species to have figured this all out. Specifically, the powers of science and the scientific community to provide insights and explanations into the most complex facets of the natural world. So appreciation of both nature itself and our own human ability to understand or make sense of that nature. And the overall goal is often about how humans fit into this larger picture of the natural world, teaching to inspire wonder, awe, and appreciation. Science education for better thinking. This is the idea or belief that understanding how science works or doing science, engaging in scientific practice, develops certain general intellectual skills. Things like critical thinking, problem solving, rational analysis, and so on. In this argument, science represents the epitome of rational thought. So having students do science will therefore contribute to the development of their own rational capacity. Science education for utility. This goal is focused on the functional value of the knowledge itself, not the process. So the functional value of scientific knowledge. And the argument here is that knowing the facts of science, concepts and theories of the various disciplines, biology, chemistry, physics, earth science, astronomy, that these concepts and theories are useful, things like the particulate nature of matter, conservation of energy, um, germ theory of disease. These are useful either personally or for the nation as a whole in terms of things like national security or economic development. And the last one, science education for democracy. This one's plain enough. It's the idea that in an increasingly scientific and technological world, citizens need to understand the basics of science in order to participate in the democratic process, to make decisions about how we collectively live our lives. This one goes back a long way and is frequently invoked anytime science education is in need of defending. So these 4 arguments for science education can be further sort of arranged by intended audience. We have sort of a technical training, sort of science for future scientists audience, and science for general education. So sort of the scientific literacy argument, science for people who aren't going into science. And if you sort of array those under those 2 audiences, I came up with 2 tiers. The most important, the technical training argument, which is science education for national utility. This is where society has placed most of its emphasis of late. Lots of talk about jobs, getting students into the STEM pipeline, and so on. And last December, in fact, the Department of Education convened the You Belong in STEM Coordinating Conference in Washington, D.C. And this launched the Biden administration initiative to strengthen STEM education with the ultimate goal of ensuring 21st century career readiness and global competitiveness. So this is the rhetoric you hear. Tier 2 is often thought of as important, but not as important. In the general education tier, the most common arguments center on these things that I listed here, with democratic participation and better thinking skills being most frequently talked about. I think most of you would agree with this characterization of the reasons we teach science. Of course, there's not going to be perfect overlap. You might divide it up a little differently or group them in other ways, but these are the things that many people believe a good science education can accomplish. But most of these are what I would call, excuse me, the myths of science education. And in the time we have tonight, I'd like to focus on three of these. First, that a crucial purpose of science education is to prepare students for science-related careers. And remember, I'm talking about K-12 education, elementary, middle, and high school. Second, that science education serves an important utilitarian purpose in students' personal lives and in their role as citizens. And number three, that science education helps students develop better thinking skills, particularly this notion that doing science helps develop these critical thinking and problem solving skills, just the act of doing it. Now, of course, bad science teaching, say having students just memorize a lot of facts in a classroom, isn't going to accomplish any of these things. But unfortunately, a lot of what happens in science classrooms is that kind of teaching. Most would argue, though, that high quality science education can indeed result in these outcomes. If you ask science teachers, concerned parents, school board members, and even science policymakers, they would say, oh, I slipped a word, I'm sorry. So what might this high quality science education look like is my point I'm trying to make here. And if you ask science teachers, concerned parents, school board members, and even science policymakers, they would say the focus should be on these kinds of things. That learning key disciplinary core ideas is important in a deep way. The ability to solve canonical textbook problems. Can students balance equations, calculate the final velocity and distance of a projectile? Is there solid hands-on work in the laboratory, hands-on being the buzzword, that's like crucial? And if we're looking at a high quality school science program, folks would say that this should include a variety of AP, advanced placement science course offerings, courses that offer experience with cutting edge engineering technologies or biotech, for example, and ideally research opportunities or research apprenticeships in local laboratories in the best cases. These are all hallmarks of what many would consider high quality science education. In fact, one of the suburbs just outside Madison recently, I don't know, it was 2 years ago, finished the $190 million state-of-the-art high school. And I'm sure many of you are familiar with Verona High School, right? The beautiful new high school that they built with the tax base from Epic and all that kind of stuff. Um, so Verona, for example, they implemented just this sort of science education program for their students. This is, in other words, the kind of science program that well-resourced middle and upper middle class communities create when given the opportunity. That's the ideal. And they trot out the three myths of science education to justify their efforts. You can just look through their websites and curriculum materials and handbooks and whatnot. You'll see that. But let's take a closer look at these. First, the technical training argument. Statements about the importance of science education for building the American workforce of the future, right? Preparing students for science careers, filling the STEM pipeline, are nothing new. Such calls go back as far as the Nation at Risk report, which some of you may be familiar with. And again, the same kind of argument comes up in the 1980s when the nation, with the World is Flat book by Thomas Friedman. These were about sounding the alarm that we're facing competition from worldwide competitors. With Nation at Risk, it was Japan and South Korea. With the World is Flat, it was China and India. These arguments were made again and again. And right around the time the World is Flat came out was the report from the National Research Council, Rising Above the Gathering Storm, which was this call to revamp science education. And this led directly to the America Competes Act of 2007 that promoted the widespread adoption of advanced placement science and math courses in the nation's high schools to meet this international challenge. Now, all this seems sensible enough. Science is the engine of technological innovation, which drives economic growth. and schools are not producing enough students ready to enter the STEM career pipeline. Problem is that that's only half true. Although science may very well be the foundation of economic prosperity, the claim about a persistent shortage of students in science is off the mark. Yet this misperception represents one of the predominant myths that drives science education, the idea that we desperately need more scientists and engineers to ensure our economic competitiveness. And you don't have to just take my word for it. We can run through the statistics. If you start with an incoming class of ninth graders, freshmen at the high school level, typical across the nation, this is 100%. Each figure represents 1%. According to the most recent data from the National Center for Education Statistics, about 50% of those students will earn an associate or bachelor's degree within the next 5 years after they graduate high school. So 2-year or 4-year degree in any subject, so half those students. And all of the associates and bachelor's degrees awarded, of all the associates and bachelor's degrees awarded, if you look at the science specific ones, it's about 27% in fairly broad definition of what counts as a science related degree. It includes degrees in everything from agriculture to engineering to nursing to dental hygiene. All of those would fall under the science related degrees. That means that in any given cohort of ninth grade high school students, only about 13% go on to earn any sort of science related degree by their late 20s. And small as that percentage is, studies show that it's over double the percentage of individuals who end up actually working in a science related occupation. One recent study looking at bachelor's degrees in STEM fields found that colleges historically produce 40 to 100% more STEM graduates than are hired into STEM occupations each year. And this is no one-off study. Data from multiple sources, the Census Bureau, Bureau of Labor Statistics, Department of Commerce, all affirm this finding about the overproduction of degree holders in science and science-related fields. In fact, a recent graphic from the U.S. Census Bureau shows this very well. On the left-hand side of the circle are all the college majors in STEM. These are 4-year degrees. Starting at the top with computers, mathematics, statistics, engineering, physical sciences, biology, and then to the softer social sciences at the bottom. On the right side are all the jobs, all the occupations that they track, not just STEM. STEM is just clustered in the upper right-hand corner. You can see where it says STEM. And if you look at, say, engineering, there's all the graduates. All the ones on the yellow path end up in not engineering necessarily, but any STEM related career. All the ones in the gray path end up outside of STEM jobs. If you go down the side, physical sciences, it's maybe 20% end up in a STEM related career. The rest not. Business, social services, legal, things like that. And the biological sciences, it's maybe what, 1/8. When you take this into account, the fraction of ninth graders who end up earning science related degrees and working in a science focused occupation, it's whittled down to a mere 7% of all high school students. That means that in a typical ninth grade science class of 25 students, 1 or maybe 2 students will end up becoming engineers, dental hygienists, or respiratory therapists. Yet the myth of science and engineering shortages continues to shape what happens in our science classrooms, resulting in more and more emphasis on student mastery of science content knowledge, the introduction of more hands-on laboratory work, and a growing footprint of advanced placement biotech and engineering courses in school curricula in an effort to increase rigor and feed the STEM pipeline. The next generation science standards, the current standards that schools are operating under, NGSS, is right in line with this. They strongly emphasize student learning disciplinary content and student immersion in the practices of science and engineering. And as such, NGSS is clearly tailored to meet the demands of the pipeline myth. And if you look at their splash page where they say why NGSS, the very first reason they give in the upper left there is because economic innovation depends on a broad foundation of math and science learning. It's the economic argument. The resulting technical training science education experience, however, does little to meet the needs of the 93% who are not going on to earn post-secondary science degrees and end up working in a science-related field. It's hard to imagine a greater mismatch between this framework and the students and families actually served by public education. Now, of course, many, and you're probably going through this right now, many would argue, well, science education isn't just about jobs. That a rigorous science education focused on facts, concepts, theories, and their practices does far more than just prepare students for the workforce. And that's true. And this is where the other two myths come in. So let's go back to those. The second myth, that science education serves an important utilitarian purpose in students' personal lives and in their roles as citizens. This is another myth, unfortunately. So why is it a myth? First off, research shows that few of us even remember the material taught in our high school science courses. Now, I'm sure all you have. This isn't a representative audience. In one study, for example, researchers at MIT found that senior physics majors scored 60% lower on a written assessment of material they learned 4 years earlier during their freshman year. Another study was with second-year medical students, reported that after 5 to 11 months, the students retained only about 60% of the basic science content they learned during their first year. And these were science majors. These were people who were interested and motivated in learning the science. This is what they already saw as their career path. Perhaps more damning are the National Science Foundation surveys found in the Science and Engineering Indicators report put out by the National Science Board every 2 years. And they do a survey, so it's really just a 10-question survey, true false questions of the general public on basic science content knowledge. And they found that fewer than half the general public, for example, know that electrons are smaller than atoms. 46%. You think it'd be 50-50 if they just guessed, right? And almost a quarter believe that the sun goes around the earth and not the earth around the sun. Now, one reason for this lack of retention is that science content is largely taught in isolation from their everyday lives. It simply doesn't meaningfully intersect with how people live in the everyday. Days go by just the same, whether it's the sun orbiting the earth and the earth orbiting the sun for them. Right? Students don't retain facts they're taught, so how could they be useful to them? And even if people do remember some of the science they're taught, rarely do they use this knowledge to make everyday decisions. Think about it. If you need to get a stain out of your pants, do you really think back to your high school chemistry class? And even if you do, will you remember what you learned about solvents maybe, or whatever it was that was taught? Or will you simply sort of look up what's the best way to remove a stain on YouTube? We're streaming on YouTube or something like that. Or perhaps you'll ask a friend or a relative, or you'll call your mom. How do I get this stain out? If the decision involves public policy, things get even more challenging. The problem is that the problems in that realm are so much more complex. Things like climate change, global pandemics, human gene editing, local land use decisions, and so on. There are hundreds of science-related social issues like these that require some form of democratic deliberation for their resolution, and all are just as, if not more complicated than the everyday personal decisions that we make. So where does school science content knowledge fit in all this? And again, I'm talking about the things. It doesn't. Over the past 20 years, studies in science education have shown that when people are asked to deliberate over socio-scientific issues, they rely not on the content that they know if they remember it, but primarily on moral, social, ideological, or ethical factors in coming to a decision. And here's research from Troy Sadler and folks who have done research on these topics. Although individuals may in rare circumstances use school science knowledge if they're explicitly prompted to or immediately after instruction, in some studies where they do things like that, they more typically don't remember the science content, don't have it ready at hand with the particular issue they're dealing with. They find the relevant content difficult to make sense of, or they don't see its relevance to the problem at all. Rather, they proceed intuitively without deliberate rational analysis, invoking personal, affective criteria and arriving at what they think is an appropriate resolution. Research in the field of science communication has reached the same conclusion, finding that scientific literacy, defined as knowledge of science content, has only a limited role to play in shaping public perceptions and decisions. Researchers have shown time and again that people are much more likely to rely on their social networks than on their high school science knowledge. When it comes to things like climate change, vaccination, energy policy, political affiliations, and what your friends and family think predominate over what's in your biology and physics textbook. An interesting study on this, some of you may be familiar with this, is by Yale researcher Dan Kahan, who found that knowing more science content, in fact, correlates with greater levels of political polarization. And so here's a graph from some of his work. He found that higher levels of science literacy resulted in correct answers to fact-based questions. You can see on the left here, this is measured climate science literacy measured in terms of just how many facts you know. The more you know, the more answers you get right. If it's fact-based, and both liberals and conservatives score well. If it's value-based, who's responsible? The higher your scientific literacy, the more divergence you get in the answers you give. And what does this mean? Kahan concludes that for ordinary citizens, the reward for acquiring greater scientific knowledge and more reliable technical reasoning capacities is a greater facility to discover and use or explain away evidence relating to their group's position. In other words, this shows that social networks matter more than science content knowledge. So the belief that knowing science contributes meaningfully to personal and democratic decision making simply doesn't square with the facts about how individuals actually use science in their daily lives. And you see this more and more every day. I mean, this really isn't news when you read the newspaper. So this leaves us with the last most common argument for science teaching, the last myth, that it promotes critical thinking and problem solving skills. And the most common form this takes is the idea that having students engage in the practice of science is the best way to develop these general intellectual skills. Now, this is a myth for a number of reasons. The quick rundown is, number one, few teachers actually teach having students engage in inquiry or authentic kinds of science activities. The second is that research experiences, when students have them, sort of like an apprenticeship in a lab or a summer research experience, do little to convey the desired understandings of science you'd like to see. And the third is that if you focus intensively on teaching scientific reasoning, if you target that and try to teach it, it often has little effect. So just run through these in turn. Historically, we know that despite all the money spent on the Sputnik era inquiry-based curriculum materials during the 50s and 60s, anybody familiar with these, right? We got PSSE physics, we got BSCS biology, chem study, created and developed by all the greats, Bentley Glass and Gerald Zacharias and Glenn Seaborg and all those folks. These were supposed to teach scientific inquiry, how science works. But follow-up studies by the National Science Foundation found that most teachers never fully implemented the inquiry teaching in practice. Most, despite the high profile and hundreds of millions of dollars devoted to this push for reform, continued to focus on textbook readings, lectures, and problem sets. When the National Science Education Standards were implemented in the 1990s, inquiry approaches were front and center again. That is, there was a hard push to engage students in doing scientific inquiry, teaching that science was a process of inquiry, yet the results were the same. Studies on the impact of the standards found that the push to hold students accountable to more and more science facts forced teachers to abandon inquiry approaches if they ever took them up in the first place. And more recent studies have found the same thing. The reason, I think, is that teachers just don't seem to be comfortable teaching this way. Few have had direct experiences themselves doing scientific work, so it's natural that they aren't sure how to engage students in this kind of work. And the fact that there are few good curriculum materials available to support that kind of work makes it even less likely. And there's a landmark study by Chin and Malhotra a few years back that found curricular materials they surveyed, a huge data set. None of them came close to capturing authentic scientific reasoning. They were just very much school-based activities. So what about getting students? That's the first part of this, that it's just not done. Teachers aren't comfortable doing it. What about if we put students in research settings? This is commonly done in summer research experiences, which have become increasingly popular at the college level in particular. Again, based on the untested assumption that doing science in these ways will somehow magically instill the ability to reason scientifically. What does the research say about this? Simply that the evidence for the benefits of these kinds of experiences is quite limited. Rather than learning about the development of research questions, how experiments might be designed to answer them, students mostly learn things like lab safety, technical procedures, and skills like culturing bacteria, collecting specimens, running data analysis, which are more job skills than scientific reasoning. A 2017 report by the National Academy on the topic of research apprenticeships concluded that the main outcomes are increasing the participation and retention of STEM students, promoting disciplinary knowledge, and integrating students into STEM culture. That is, these things just really are a form of professional training or job shadowing. There were no positive outcomes associated with better thinking skills reported. All right, what if we target, let's teach specifically scientific reasoning. Can students be taught how to reason scientifically? In intensive, carefully designed instructional settings, the answer is kind of. Studies have shown that under ideal conditions, students can learn some aspects of scientific thinking, but with respect to the key features of experimental design, students typically struggle to create controlled experiments on their own, typically manipulate too many variables at once in a given experimental setup, and cling to prior beliefs in the face of conflicting evidence. In a summary of research on teaching scientific reasoning, this came out in 2020 in the Annual Review of Developmental Psychology, Stolman and Walker found that looking at all these targeted approaches, they found that there doesn't appear to be a natural developmental path toward higher levels of scientific reasoning, nor do there seem to be any obvious instructional strategies to help students easily learn the skills involved. And the challenge is fairly obvious. Developing scientific reasoning in students is difficult because scientific reasoning itself is difficult. The eminent biologist Lewis Wolpert famously made this point in his 1993 book, The Unnatural Nature of Science. He explained there that the towering achievements of science are so remarkable just because the thinking that led to them goes against the grain of common sense. But even if we could get students to master the processes of scientific reasoning, it's highly unlikely that this would lead to better everyday thinking, transfer, the idea that there's transfer, which is the argument that's made. The reason for this is that the natural thinking people engage in on a daily basis, every day, that Wolpert talked about, operates with a completely different set of cognitive skills and dispositions. People approach everyday problems using intuitive shortcuts, heuristics, and emotions that are largely tacit and invoked unconsciously. And if we do stop to engage in a careful rational analysis, such efforts are overwhelmed by emotion and personal bias. Some examples of the research that documents that. The lay public has always relied on this intuitive gut level moral reasoning. Over 130 years of formal science education hasn't changed that. In fact, it's this continued reliance on intuition rather than hard evidence that's resulted in the very problem we currently have. That it seems to make sense that doing science, the ultimate rational enterprise, will result in better thinking skills. This is what we intuitively believe. But it's not that simple. So, to recap, career training, everyday utility, critical thinking skills, skills that are believed to be essential to the processes of democratic deliberation. These are the myths currently driving science education in this and most other Western countries. Except that the science education we have in our middle and high schools, heavily focused as it is on content mastery and technical training, is useful for almost none of these things. We don't need more scientists and engineers. People don't need detailed science content knowledge to solve their everyday problems. And folks just aren't very good at making carefully thought out rational decisions. To put it in terms of the original purposes of science education, we can effectively cross those off the list. So is exposing these myths an argument against science teaching? Absolutely not. I'm very pro science education. The look around us tells us that that can't possibly be the case. The challenges of global pandemics, climate change, safe water supplies, and countless other science-related social issues are beginning to overwhelm us. Clearly, we need some understanding of science in our modern society. But ratcheting up the rigor, teaching more science facts, concepts, and theories, having students do science or engage in science and engineering practices isn't going to do the trick. Going faster along the same rutted path is going to only end up getting us stuck in the end. But if science education can't do what we thought it could, then the empirical evidence certainly seems to confirm that it can't. What can it do? What is science education actually capable of? And I believe the key to answering that question lies in giving up our vision of the rational individual and acknowledging the role of expertise in the modern world. So what does that mean? First, we need to recognize that scientific expertise is an inescapable fact of modern life. We all know this when you go to get your car repaired, right? Somebody's expert. You're not. You just have to trust them. The late science educator Stephen Norris wrote very insightfully about this. There is almost no situation in which individuals can make or have the ability to make first-order judgments about whether a scientific claim is valid or not. In other words, people talk about, I teach science in my class so they can pick up the newspaper and read something and decide whether that's true or not. You can look at the evidence. Scientists themselves rarely feel confident reviewing research outside their area of expertise. If that's the case, how on earth can we expect the average person, no matter how many school science courses they've had, to be able to determine whether some scientific sounding claim they've read in the news is legitimate or not? They can't. As Norris wrote, non-scientists are inescapably dependent for their scientific knowledge upon scientists. Whether or not something counts as scientific knowledge is not a decision non-scientists are in a position to make by themselves. All they can do is rely on experts to help them understand and help make their decisions. No amount of science content learning or school science lab work is going to change that basic fact. And I would argue that we need to imagine a new goal for science education, building public trust, which builds on and extends the goals of democracy and cultural appreciation. We need a science education that addresses the troubling tendency these days to mistrust and discount scientific expertise in areas where expertise matters tremendously. Two key shifts in science education are necessary, I think, if we hope to realize this goal. First, let's get rid of the focus on facts and technical skills that are only relevant to the 7% of students who will go on to science-related careers. Let's teach instead, how are facts made? How do they come to know what they know about the natural world? We should dedicate ourselves, in other words, to a renewed focus on the epistemology of science, how we know what we know. Engage students with questions about that. How do we know? What evidence do scientists have to support the key models and theories they have about various aspects of the natural world? And with this new focus, we should highlight the diversity of scientific practice in our teaching. And this is a point that's almost completely overlooked. Science isn't conducted according to a single set of practices, as NGSS would have you believe. And it certainly isn't done using some monolithic scientific method, though that idea has had remarkable staying power over the years. Science is a general way to describe a wide variety of research communities, each of which operates with its own distinct set of practices. The work being done in fields such as epidemiology, climatology, experimental physics, evolutionary biology, such fields couldn't be more different from one another in terms of the phenomena being studied, the methods of data collection, what counts as evidence, and the nature of the theories and models developed. Let's allow students to look at how science works in these and other fields, not by some false imitation of science, of practice, by reading about and seeing and talking with the researchers who work in these fields. Understanding the varieties of scientific practice is crucial for disabusing public belief in a single method of science, which is often believed to be experimental and capable of unambiguous confirmation of claims. That belief that you can always prove something, where's the experiment? Show me that this actually happened, is why it's been so easy to undermine public acceptance of things like evolution, climate change, and the carcinogenic effects of smoking, as Naomi Oreskes and Eric Conway write about in their book Merchants of Doubt. All of those sciences rely on indirect evidence and non-experimental methods. Second, in order to help students face the challenges in our current day, what we need isn't to arm them with some set of scientific facts, but rather to help them develop a deeper understanding and appreciation of where science knowledge comes from, how it's funded, and which institutions, and why we can rely on it for making personal and public policy decisions. This is what I call the institutional context, teaching about the scientific enterprise, not just the facts of the various disciplines. This would mean talking about how research priorities are determined, the role of peer review, how funding sources influence the nature of research that's done for good and ill, the way scientific research is regulated, who does science, what it takes to enter the profession, and how institutions and agencies like NSF, NIH, the CDC, the FDA function in society. Why is it there's no place currently in the school curriculum to talk about these agencies that shape so much of our lives and interactions with science, and that are at the very center of current science society conflicts? It just baffles me. Now, I admit that much of what I'm calling for is well beyond the scope of what we currently think of as science education. Teaching how scientists became convinced the Earth's surface consists of moving plates isn't a real stretch from a traditional perspective. A little more historical narrative to go with the details of the current model of plate tectonics is all you need. Looking at the cultural consequences of Galileo's arguments for a sun-centered solar system is more of a lift, but there are decent materials out there that teachers can draw from to teach that idea. Taking on questions about the public role in setting research priorities, how scientific institutions function in society, however, would be entirely new and exotic without question. Yet making these things the focus of instruction is crucial if we hope to shift public perception of science from being viewed as something outside of society and culture to being viewed as an integral part of it, as something that citizens themselves have a role in shaping as legislators, school board members, community leaders, and voters. With this, we can achieve a dual purpose: science education for culture's sake and for a kind of cultural appreciation that leads to a more effective democratic participation. That's my vision. But if there's only one message that I'd like you to take away from this talk this evening, it's that what we're currently doing in schools is not this, and it doesn't work very well. Our continued focus on science content knowledge and the doing of science, given what we know about how students learn and how people use science in their daily lives, simply makes no sense and more than likely is counterproductive, pushing more people away from science than drawing them in. And I think it's time we took a hard look at the evidence. What does it say about what's actually possible to accomplish in science classrooms and then build our science education accordingly. And with that, I'll stop. Thank you for indulging me.
So if anybody has any questions, just raise your hand and I will bring you the microphone.
Well, I want to thank you for depressing the hell out of me. Um, the one thing that I wanted to ask you about is the role of the internet today in science education, because I'm seeing it as a twofold process. Because you would think the internet being a wonderful democratization of information and people being able to access all the science out there, that it would be strengthen our scientific knowledge as a society. On the other hand, it also provides a forum for people to find communities where they can, those people that, you know, take correlation as evidence of causation. And, 20 years ago, exactly 20 years ago, someone that said the earth is flat would have just been labeled as a nut and probably put away. Now they can find a community of other people that believe this, and they can push pseudosciences out there. So how does the educational system deal with this dichotomy of the internet and what you can do on the internet?
Yeah, that's a great question. There's definitely a push in science education. In particular, there's a group that got together last February or February before last at Stanford that was looking at this issue of misinformation and how the NGSS doesn't address it at all. It just says learn science content and do practices, and then you'll be fine. And all these things will not be a problem. And the group was looking at science misinformation, and this is Sam Weinberg and folks at Stanford who've developed um, strategies and research-based techniques. How do you, right? So you say all the science is out there on the internet, so is everything else. And so the question is, who do you trust is what the question ends up being. And if we don't talk in our science classrooms about what are the institutions and the sources that we can trust and rely on, students don't know. It looks official. It looks, or the people, not just the students. And so there needs to be, I think, that move to think about how do you develop that understanding of where legitimate knowledge actually comes from. Um, and that needs to be a new focus in what happens in educational settings, because everybody just sits and, how many times you're in a group of people and it's, oh, that's interesting, let me Google that, and a bunch of stuff comes up. And all of us know that you can scroll through the nut stuff and get to the, oh, this is the real stuff. And it's sort of a very subtle tacit kind of knowledge that we have to be able to sift through that, because none of the stuff out on the internet is curated like it used to be before the internet. Yeah.
Hello, thank you. I'm rising high school senior, so a little bit able to connect to this on a personal level. I was wondering if you think that there's a role for students to play in this, and if so, what is it? Because a lot of this seems like it's affecting us. Like, I know that this is affecting students. And in order for something like this to change and to be better and to make science more interesting and accurate for students to learn, what do you think we have to do to move that ball forward?
Yeah, I don't know that there's anything. It's hard enough. Honestly, this what I'm projecting is this is what we should do. It's almost impossible to actually do, right? There's these ruts that teachers teach in the way they teach because it's easy to teach that way. It's easy to assess students. Everybody's happy, right? Student gets a 4 on their AP test, they're happy. Their parents are happy. The school board's happy. They've gotten that credential. They don't have to buy that credit when they get to college. So the fact of what they actually learned, if it was just a bunch of facts in the AP Chem class or the AP Bio, I'm not picking on any of those in particular, um, doesn't matter, because all they're worried about, all people are looking at is the credential, the check mark, they're not looking at what's the value, the inherent value of what is being taught. And so there's all parts of the system that are aligned against doing this. And the way we prepare science teachers, like I said, the teachers that come, the candidates, pre-service teachers that come into our program, all we say is you have to have an undergraduate degree in a natural science. Okay, they've gone through this system where they focused on content, they memorized content, they got good grades. And so they're naturally disposed to teach them way. I want to help my students get good grades too. And I can explain things really well. And I can do activities that'll make them understand the various quantum levels of the atom, despite the fact that they'll forget it. The students will forget it, 3 months later or longer. So I don't know what students can do other than that's a great question that I don't have an answer for. I'm sorry. Yeah.
I have a question. I have
Yeah.
really one comment and one question for Kevin. I think part of the problem with the internet is it allows everybody to listen in to the internal debate of scientists.
Yeah.
And that's very confusing. And though I love archive.org, there is so much stuff out there where our people are holding the internal debates about things. And there's no way for anybody, even somebody who has gone through something that you are advocating for, to really make a decision about who's right and what are you going to quote and what aren't you going to quote. But my question was, about 30 years ago, Robert March produced his Physics for Poets.
Yeah.
And I'm curious what you think about that approach to dealing with science education.
Yeah. I'm familiar with Physics for Poets and Robert March. I'm more familiar with Gerald Holton's work. He did Harvard Project Physics years ago after PSSC. He felt that this is just science for scientists. We need to have a physics curriculum for everyone. And he came out with that. Actually, it was based on Holton's freshman Harvard physics class. He wrote a textbook, and then he brought on Jim Rutherford, and they expanded it and had this Harvard Project Physics, which is a historical approach, cultural approach. That's exactly the kind of thing that would be better than what we currently have. I look through all the various like AP guides, content guides for all the courses, and you look at current textbooks, and almost none of it has any. There used to be a lot more history of science and understanding the nature of science and philosophy of science in these science textbooks, and a lot of that came from these folks. And so Holton and Rutherford, who did Harvard Project Physics, it's interesting the way this um, Holton was a physicist and a historian of physics, obviously, and they developed that curriculum project, that textbook, and then Rutherford, who started in the history of science at Harvard, uh, eventually came to direct Project 2061, Science for All Americans, which uh, actually has the sort of closer idea of this kind of approach, science from cultural and philosophical perspective, and understanding what science is rather than just the facts of science. So I think if we can get back to that, but it's hard because that's not where we're going, because it's all about the STEM pipeline.
It's a wonderful talk. It's depressing. I've represented humanistic scholars for much of my professional career. And they're all crying and they're jealous of you guys. They can't get funding like you guys can get. I mean, it's a whole litany that goes on. Who are your allies in the university? This is a bold vision.
You
Do
know,
do you have friends and fellow travelers
got some friends.
in other disciplines? I'm thinking about, especially the humanities.
Yeah, I mean there's a group. It's interesting. I've given a version of this talk to a number of different audiences, and I've gotten some very hostile reactions, and I've gotten some very sympathetic reactions. There's a group censor, which is I don't know what it is exactly. It's a Society for Environmental something Science and Society kind of group internationally, and they were very sympathetic and supportive. And a lot of them said, "Well, you're not telling us anything we don't already know." And I'm like, "Well, good. I'm glad you're all on board. Let's keep working." Uh, and then, interestingly enough, I gave this talk a few months ago to the current group at BSCS, uh, and that's where I got the most hostile reaction. They were like, "Well, we need to prepare students for STEM careers. The current director, Danny Edelson. And I'm thinking to myself, you should go back and look at the origins of this project, because that's not what it was about at all with Bentley Glass and Arnold Grobman when they were first developing this. It was all about developing a scientific literacy and understanding of what science is, not just cramming in the facts of science. And all of them had to fight, like the TSSE project. They left out so much physics, but they treated what they did in a coherent whole that showed the interconnections and nature of physics and what it was about. Um, so there's people working, this group at Stanford, they're working on this. There's a lot of editorials coming out, and we're trying to push NGSS in this direction to address these things that are not being addressed. I've got an essay coming out in the American Scientist in July on scientific literacy, which makes this argument in a different form. So just keep working, get up every day.
I'm getting old. Back in the 60s, when I was at the university, everybody was excited or upset about what was going on in Vietnam.
Yeah.
And I took several courses in East Asian political science and history because I wanted to understand what was going on. And I took one class, and the professor said, if you read something, you don't know what happened. He said, I want each of you to pick an event that happened in East Asia. It got a lot of coverage. And then you have to do research, go to every source you can find that reported on the events of that event, and keep track on each source what facts everybody agreed on. Because everybody that reported had an axe to grind. And what you didn't know what happened just by reading a report or a couple of reports. You had to see what was consistently true in every report that you read. It was eye-opening. I wound up reading newspapers, English language versions of newspapers all over Asia and the rest of the world. And as I read what the topic was going to be this evening, I thought about Copernicus and why he thought that the Earth went around the sun. The consensus at the time was the opposite.
Yeah.
And he was criticized for what he believed. And I think if you look at the history of the Nobel Prize, you're going to discover that almost everybody that got a Nobel Prize got it because he thought of something that was different than what everybody was thinking at the time. And it was making people realize that there was a different way of approaching it, is what we should be teaching kids in critical analysis. You can't just believe what one person tells you.
Yeah.
Because in every one of those Nobel Prizes, there was a consensus thought that was wrong. And you have to understand that I majored in psychology, haven't used it since, but it had a tremendous insecurity complex about whether it was a science or not. It was all they talked about was scientific method, and you had to do this. So what I did learn was the scientific method and how little it's used outside of psychology. I think that would be where science education should consider going to make people better citizens.
Yeah.
Thank you. Thank you very much. Good evening. Being the mom of a rising senior, and looking at potentially being interested in science or not, when you're looking at colleges for science, what are you looking for when you're not looking for, um, oh, you teach great physics, you teach great biology. What are you looking for in their science program that they're valuing
Yeah, I mean, that's hard to say. Like, I don't know what goes on at all these different colleges. I guess I would say two things. One is you might be better off at a smaller liberal arts college than a large research university, uh, just because there's more attention to teaching, I think. The other thing I would say is if you're asking what can the student do, if you're at a larger institution and science is your focus, then don't just take courses in science, right? UW has a wonderful history of science department, used to have, but can't folded into history. It's got wonderful philosophers of science. So I would take the science courses along with the history and philosophy, sociology of science, and get a bigger picture, a broader picture of what science is and what it's all about.
So I really enjoyed this presentation and found myself increasingly agreeing with more and more of what you're saying. But I kind of feel that you're limiting the scope and bearing the lead a little bit. If you go back to your second myth, you showed a bunch, you don't need to, I just
Okay. Yeah.
rhetorically, you showed us a bunch of rapid fire evidence on the screen of papers showing the second year medical students don't remember the first year, but we teach all the science and people just lose it all right away. I think if we expand our focus, that is true of history, that is true of English, that is true of math, that is true of everything we teach in secondary education. So we kind of have to ask, what is the point of all of this besides just teaching kids how to sit at a desk, do work, and have a boss?
Right. Right. I think the difference is um, part of the problem is that, and we talk about this in the with the first year method students, is that one of the exercises I give them, they get in their disciplinary groups and I say, all right, you're working in the school district. You just found out there's been a budget cut. You're the physics set of physics teachers. You only have one semester to teach everything a student needs to know about physics at the high school level. Give me what a course looks like. Same with the biology teachers, chemistry teachers. And what the students do is they take everything, essentially the textbook table of contents, and they just try to cram it in, right? And that's what happens now is that people think they have to cover everything in the textbook. And so, and you can do that. Students will memorize stuff. They'll do well on a test and they'll work, they learn mnemonics, they learn all kinds of things to get right answers. And teachers teach them how to get right answers without really understanding. Like, oh, let's do this. Put this term here, this term here, this cancels, you'll get the right answer, even if you don't understand why. Um, and so if we scale back, if we teach, like what are the real big ideas in each of the sciences and teach it well and teach it in context and teach where it came from, I think they'll remember it than the way they currently learn it. So that I think it's a different approach and a different focus, and it's not just on all the topics and content that exist.
I think we're going to need to make this our last question so John can get on with his weekend.
Thanks. So, kind of going off of the last two questions, is this really more just a challenge to the idea that the purpose of education is job training and STEM is just sort of brand of education is job training? It's the one that everybody talks about, it's the one that everybody pushes. And when you're looking at colleges and you want a well-rounded education, is it the quality of the STEM program or is it they've been dropping all the humanities programs left and right the last 5 years? What is like I kind of I agree with everything you say. I don't think it's specific to science. I think it's just in general this idea that the role of education is to train employees.
Yeah, I think that you're right, and I think that science and STEM is a particular example that is sort of supercharged by that idea. And it's based on this universally accepted notion that, oh, we just need more technology and more science and everything will be great, you'll get good jobs, the economy will grow, we'll beat our competitors globally. And no one's and people just aren't looking at that rhetoric is so powerful. And a lot of science educators feed into it because it gets funding, it gets funded, right? So you make that argument because you know you'll get money. Um, and that's the challenge is to try to think differently about schools. Shouldn't be about it should be about like, how do we, at the K-12 level, we should be preparing citizens, right? We're not training workers. Like, and some people disagree with me, right? And that's fine, but I don't think that that's what education was originally developed historically to do in this country. It was about the republic and preparing people to be engaged because it's a democratic society and you need educated people to participate in that. But yeah, I agree. Yeah, thanks.
Thanks, John. Can you hear me? Yeah, please bear with me. I'm going to ask you some kind of weird questions. John, how do you spell mop?
MOP,
Yes.
MOP,
How do you spell shop?
SHOP,
What do you do at a green light?
you go.
No. What are you thinking?
I memorized that answer.
Trump really inspired me, I kept getting the impression, we could really use a paradigm shift when it comes to educating young people. And it occurred to me, some of the best science I learned was learning about how my mind works and how other people's mind works and how the human mind can be filled like magicians that worked during World War II to create illusions to fool the German army or concepts like that and things have a class where Professor Penn and Teller come in and teach kids this is all the fun ways that you can trick people. And these are all the fun ways that people can attempt to trick you. Be mindful of it. Learn about confirmation bias.
Yeah.
Learn about philosophy. What's a valid argument.
Yeah.
Things like that rather than drilling people full of facts. Just teach them how to fish.
Yeah.
You're very inspirational talk tonight. Any comment on my thoughts, bring forth any.
I get all kinds of supportive comments like that, and it's funny how when you speak to a group, it makes you wonder why it's not different, because so many people think, oh, this isn't what it should be about. We should really be thinking about doing it this other way, and so it's the resistance to change is really puzzling and difficult. Yeah.
You're much like somebody coming in, hey, I've got this neat invention called the photocopy. And they try to sell it to Kodak, and Kodak says, that's not how you do pictures. That's not how you do imaging. And they throw it out because it doesn't make any sense to them. So
Yeah.
that's the kind of resistance that can happen with
Yeah.
those paradigm shifts. But John, on behalf of Madison Astronomical Society for such a great presentation, a little token of our esteem, this mug.
The mug.
The Madison Astronomical Society logo on it.
I love that. That's great. Thank you.
On behalf of the society, I'd like to wish you the best of luck with all your these are very great efforts that you're making and how to reimagine education. Thank you so much. We wish you all the success. Thank all of you for coming. Well, on behalf of the society, that is the end of this meeting for this month. We'll see you back here on the second Saturday of July. Next meeting. Does anybody remember what date that is? In front of it. So thanks everyone. We will see you next month. Safe
Yeah.
So you being honest,
Yes. Both you smart size. No.
first year without having room.